This video is a short introduction to the Mathematica package xCoba. xCoba is part of xAct, and in a previous video we have presented an introduction to another package of xAct called xTensor, which has been written in order to do abstract tensor computations in differential geometry. xCoba extends this package so that it can be used for doing computations of tensorial expressions that involve chosen charts or bases in the tangent bundle of a manifold. So the absolute prerequisite is to actually listen to my video Introduction to xTensor in order to have the basic knowledge of the xTensor package, unless you already have it. And as is also explained in that video, you have to install xAct. It's not part of Mathematica. You have to download it and install it in your system. Some very brief instructions are shown here, or watch more details in that video. The package needs to be loaded in your Mathematica session, so start a new Mathematica session and load the package with this command here, with this function. So after it has been loaded successfully, you will read all those messages here. And the first step is exactly the same as the one used in the xTensor package. We have to define a manifold with the function defManifold, exactly as we have done in the previous video. So we call defManifold with three arguments. The first argument is the symbol that we use for the name of the manifold. Here we use the symbol capital M. The second argument is the dimension of the manifold, and the third is the list of the allowed indices that will be used for any tensorial expression that we will write that refers to the tangent bundle of that manifold. So if you remember the function dim of manifold, it displays the dimension of the manifold. Therefore now we can use we can use the variables or the symbols dim m or dim m1 in expressions that will refer to the number of dimensions and the number of the spatial dimensions of our manifold. So then what we will do is we will define a chart to work with. For xCoba, a chart is synonymous to a coordinate basis. In fact, xCoba knows nothing about charts and their global structure. It only works in a tangent bundle. So when we use the terminology of a chart, is actually the choice of a basis, and it has on top of any other basis the properties that the coordinate basis has. For example, it's a Lie bracket. The Lie bracket between any two vectors of that basis is equal to 0. Now we will see that with each chart or each basis, xCoba associates a particular color, and that helps us read easily the output of tensorial expressions and understand from the color of the indices to which chart they refer to. So let's see the command that will define the chart that we will use. We use the function defChart for defining a chart. The first argument is ch. It is our chosen name for the chart. We just use the first two characters of the word chart, that's all. Then m is the manifold that this chart is defined on, which is the manifold M that we defined before here. And the third argument is a list of numbers that refer to the allowed values that the indices of the components of tensors take in this chart, or equivalently the indices that are used in order to enumerate the basis vector of the tangent bundle. So we have chosen 0, 1, 2, 3 to follow the convention of space-time physics, but you can choose any number, whether it is sequential, any set of numbers, whether it's a sequence of numbers that 0, 1, 2, 3, or any other number that you would like to have. Now the fourth argument is a list of scalars. So you see there are some symbols here that refer to the names of the coordinates t, r, theta, and phi in our case, and you see that we also use the square brackets that will define in the xTensor notation scalars on the manifold M. So we think of the coordinates in this setting as being scalars defined on the manifold M. The last argument is an option that defines the color that is associated with the chosen chart and its associated coordinate basis to be blue. This argument is optional, and if we don't use it, then a default color will be used with the package will use a default color to color our basis. So after this, after we call this command, after we execute this command, we see some messages here that gives us already some information of what is done under the hood. You see those messages here say that the scalars t, r, theta, and phi have already been defined. We don't have to give an explicit command for that. And then there is a so-called parallel derivative defined for this chart. It has the name capital PD from the initials of parallel derivative, then the name of the chart, and then you see there is a contravariant index minus alpha there. Also there are Christoffel symbols, Riemann tensors, and Ricci tensors that are defined with respect to this parallel derivative. Now, what is the parallel derivative? In our case, where we think of the chart as defining a set of coordinate bases, this is the ordinary partial derivative with respect to the coordinates that we have chosen. Now, this is a more general concept because this parallel derivative is also used for non-coordinate bases, and then this parallel derivative is something like a connection that is used as a reference connection associated with the choice of this basis. But we will not get into that in this video. So after that, we can use xTensor commands or functions to define particular objects. So for example, def constant symbol will define the symbol mass to be a constant symbol, and this is constant with respect to differentiation. You remember the option print as. So after that, the symbol is defined, and whenever we use it in an expression, its standard form here in the output is what we have put here to be printed as. So that is a nice way not to use very simple symbols for different parameters, but to have a nice output in our tensorial expressions. this is a call to a function that defines a scalar. So now scalar is a scalar field, but you see that because of the print as option, it's printed as a file. Of course, we can define scalar functions without giving any print as option here, like in this case with s, and whenever we use s in an expression, then it will just print the name of the symbol that we have used. We can also define tensors, like in our case, we define a vector w here. You remember this from the xTensor package. All we have to do to define a tensor is to choose a name, a symbol for it, and then put the indices in square brackets, and write here the manifold where its tangent bundle is over. So now we can use expressions that have all those symbols. For example, let's write 2 times mass divided by r. You see how this is printed. You see that the coordinate functions are printed without the square brackets, but we have to remember to put the square brackets in expressions that involve them. Now this is another expression, r times s times scalar times w nu. So you see the result, but this is nothing new. It's exactly the way that we have defined geometric objects in the xTensor package. So you see that in xCoba we can use xTensor objects in our expressions, and they will be used accordingly. We will see several examples in what follows. But the reason that why we use the xCoba package is because we have to compute expressions in a particular chart. For that, we have to define a particular tensor object in the sense of the xTensor package, which is called a C-tensor. C from Coba, and tensor for being a tensor. So let's look at an example here that defines a vector. So the call of CTensor here defines a vector with that is referred to by the symbol v, and we use here 2 arguments. The first argument is the list of the components of the vector in the chosen basis, and the second argument here is a list of the chart that the components correspond to the particular index. Now we have only one index, so here we only have to put the name of the chart ch here. So this is a vector whose components are 2, -1, 3, and 4 in the chart ch. So you see that when v is printed, we see something that has as head the word CTensor, and then here we see the arguments that correspond to its components, the chart where the indices, corresponding indices correspond to, and then we see here another argument that we have not put here. It is the weight of the tensor. So for ordinary vectors the weight is 0, but then we can have tensor densities that have a weight that is different than 0. So the standard form of a vector is printed in this way. that we show here. So now that V has been defined to be a C-tensor, we can use the xTensor notation to write it as an abstract vector. So since this is a vector, it takes one of the indices of the manifold M. When we put no sign, this is a covariant index. A minus sign refers to a contravariant index. In our case, we just have a vector, so that is an upstairs index. So you see how it is printed here. It's printed as an abstract xTensor object here, but the head that is printed here is not V, but the components. So writing any tensor in the xTensor notation here displays also the components of that vector in the chosen basis. So this is one way to see the components of a vector here, but later also for more general tensors. But CTensor can do more things than an ordinary tensor object of the xTensor package. In fact, instead of just taking an abstract index, like in this expression here, it can take two different types of indices as well. The other indices differ from the abstract index by being a list and not just a symbol. So we have a basis index which is a list of two elements. The first element is the symbol of the index of the basis, and the index of the manifold, of the tangent bundle. And this should be one of the indices of the manifold M. And then the chart that this index refers to. So we can write our vector here, which is a C-tensor object, by putting here this basis index, mu ch. Now, what this expression will evaluate to is the vector v as a linear combination of the elements of the basis of the chart ch. So you see here this linear combination. Now the basis vectors are E0, E1, E2, and E3. Now these numbers 0, 1, 2, 3 are taken from the list of the definition of the C chart here. It's all the numbers that we have put in that list. And since they are vectors, they also have an abstract index nu. Now, because the components of V in that basis are 2, minus 1, 3, and 4, it is a trivial fact that this is the linear combination that gives us the vector V in that basis. So you see that using an abstract index on a C-tensor object has a different effect from using a basis index. Now, another type of index is to use a component index. A component index can be used in order to extract a particular component of a tensor, here a vector. So this is different from this differs from a basis index from the fact that instead of using a symbol that is one of the indices of the manifold M, we use one of the numbers that are in the list of numbers of the chart. So in our case, those are the numbers 0, 1, 2, and 3. So for example, we can use the expression V and put here the index and ask for the 0th component in that chart. by putting the 0 number here for the 0th component and ch here for the name of the chart or the basis. So that will give us the first component of the vector, which is equal to 2. So you see it's 2 here, 2 here, and 2 there. Now if I put here a 1, I will get the second component, which is equal to -1, as you can see here. And if I put 2, I get the third component, which is equal to 3. And if I put 3, then I get the last component, which is equal to 4. And of course, these are the only allowed values that we can use for a component index in a C-tensor object. So let's work out another example. Let's define now a one form. So a one form as a C-tensor object is defined in a similar way. The difference being here that we indicate that this is a one form instead of being a vector by putting a minus sign in the list of charts. So we have minus ch, therefore we have only one index, and because of the minus sign, this is a contravariant index giving us a one form. Now -2, 1, -4, and 3 is a list of numbers that gives us the components of omega in the basis ch. So again, we can write similar expressions for the one form as we have done for the vector. So we can use an abstract index, and then we can see the components displayed in this form. See also where the index mu is displayed. So that shows us that this is a tensor object, it's not just components. Here we use a basis index, and in this expression it will give us omega as a linear combination of the basis one forms or the basis covectors. Now look at the difference between the expression here and the expression there. So the indices 0, 1, 2, and 3 are colored in blue, as in the case of V, because that is the color of the chart. And the abstract index, mu, is now downstairs. And of course, the indices of the bases are put upstairs. Notice also that in order to indicate that this is a contravariant basis index, we have to put minus signs also in front of the symbol used for the index and in the symbol used for the chart. Now we can also write down the components of omega using component indices. Here we use a table to construct a list of all the components. So we write now omega alpha comma minus ch, where alpha goes from 0 to 3. So be careful here, alpha is not an abstract index as it is in this expression, because when a table expands this expression, alpha is substituted with all the numbers between 0 and 3. So here we will have, in fact, omega 0, omega 1, omega 2, and omega 3, as it can be seen here. Now that we have a one form and a one vector defined, we can do contractions. So for the contractions, we can use the xTensor notation, and we can write the one form omega with a downstairs index minus mu, and v with an upstairs index mu here. So that will make the contraction and will give us the result, which is equal to -5. But contractions can be done not only between C-tensor objects, but between mixed objects that involve both C-tensors and ordinary tensors that are not C-tensors. So here is an example. We contract the one form omega with the vector w, and you remember that w has been defined above with the def tensor function here. So this is a tensor in the xTensor package sense, but not the C-tensor. So let's see what the result will be. Now look how this is written. You remember from the xTensor package that w mu is printed in standard form by writing the symbol w and the index mu upstairs or downstairs, depending on what we have put inside the brackets. Now, the second term here is omega, and you see it is also written in an abstract notation by putting the index mu here, but the head of the expression is not the symbol omega, but the components. So we can see this contraction in a more explicit form by using the function to basis expand. So you see that in this case, omega here is expanded as a linear combination of the covector bases E0, E1, E2, and E3. And you see that we don't obtain a scalar yet because the basis vectors have not been contracted with the vector w. So in order to force the contractions between the elements of the basis and the abstract tensor w, we have to apply the function contract basis. So you see now that we obtain a scalar expression that involves only the components of the vector w in the chart CH. The numbers here, the explicit components of the one form omega. You see now that the tensor object w, the abstract tensor w, is now displayed in terms of its components in the basis CH, indicated by the blue color of its indices. So now we can do ordinary algebra between tensor objects using the xTensor notation. So for example, we can write 3 times v. And we will obtain this result here. And you see that the component, we obtain a C-tensor object here, whose head now contains the components of v, but they also have been multiplied by the scalar number 3. So we can add this w mu. So again we obtain an expression that involves tensor objects in the xTensor notation here. And we can also write down tensor products. So tensor products in the xTensor package are written as ordinary products in Mathematica, and the tensors here must have different indices. So you see now that the result is is a 2-0 tensor object here with two abstract indices, mu and nu, coming from the tensor product, but the head now contains all the possible products between the components of V that correspond to the components of its tensor product. Now notice that this 2-0 tensor is displayed within a blue rectangle, and the two lines, the two vertical lines and the two horizontal lines, correspond to the color of the respective indices mu and nu to the basis that we have chosen, which is the blue color. Now, if we have other bases in our calculations, we might see mixed indices with different colors on each side. So the vertical sides might have one color and the horizontal sides might have a different color. Now, this is another example here. That is the tensor product of the one form, omega, with the vector v. So you see we obtain a similar output, but notice the indices, mu and nu. Mu is downstairs and nu is upstairs. And we can make also contractions. We can also form a tensor product between the vectors v and w, where w is not a C-tensor object, but an ordinary tensor. And we will obtain a similar expression as in the xTensor package, except that the head of the vector v is replaced by this column display of its components. Now, all these expressions here can be seen in a more explicit way by applying, for example, the function to expand, to basis expand. So if we take this tensor product and we apply it to basis expand, we obtain this 2-0 tensor as a linear combination in the 2-0 tensor space that whose basis is just the tensor products, all possible tensor products between the basis vectors. In this case, we have tensor products between basis vectors and basis one forms. And similarly here, we have this tensor product here, and that is the best we can do. So that is the linear combination of 4 tensor products of W with the corresponding basis vectors. We can assign vectors using the equal symbol as in ordinary Mathematica expressions. So for example, we can say that the vector U1 is equal to V, where V is a C-tensor object. This is not recommended for tensor objects in the xTensor package, but we can do that in the xCoba package. So now U1 is a vector that is actually equal to the vector V. But we can do better than that. I mean, we don't have to just equate two vectors like that. We can form expressions like 2 mass divided by R times V. That defines the vector here after doing the scalar multiplication. there is another function that is called CTensor. So we can use this to transform C-tensor objects or ordinary tensor objects to any basis that we would like to. In our case, we just have one basis, so we will use C-tensor to form a C-tensor object from the ordinary tensor W. So W is an X-tensor object defined by def tensor. With two C-tensor, WCH, we form a C-tensor object that has components W0, 1, 2, 3 in the chart CH. And we can assign that to another symbol, like let's say W1. So W1 now can be used the same way as any other C-tensor object is used in any expression that we would like to form. So this is another example of using CTensor. So you see that we use the function CTensor to create a C-tensor object from the tensor W, the vector W. And after this has been defined, we can use it as any other C-tensor object and multiply it by the scalar 1 minus 2 mass over R. So you see that the vector U now has components that are equal to the components of W multiplied by the factor 1 minus 2m over R. And then U can be used the same way as any other C-tensor object. For example, here to compute the contraction of U with the one form omega. So it doesn't really matter how you use C-tensor, you just have to put it in expressions where any other C-tensor object would be legal to exist at that place. So here we form an expression that has a scalar, a C-tensor object, and divided by another scalar. And you see that the result is as expected here. The components of the C-tensor object being the list in the first argument of the C-tensor object. Let's define a higher rank tensor. So this is a U02 tensor. First of all, a U02 tensor has components that form a matrix, and therefore the first argument is a list of its components, the same way that we construct a list of the elements of a matrix. So it's a list of lists of numbers, where the lists here correspond to the rows of the matrix. The fact that it is a U02 tensor is determined by the second argument that has the name of the basis those components are referred to, with a minus sign in both elements of the list. So if there were no minus signs there, B would have been a 2-0 tensor, and if there was one minus sign and one with no sign, that would have been a mixed 1-1 tensor. So this defines the tensor, the C-tensor object as shown here. And then we can use the B tensor in expressions like this one. Now this is with an abstract index, and that will display the tensor with the head formed by its components and the two downstairs indices, U and U, which are abstract indices. And if we act with to basis expand, then we will see B as a linear combination of the basis formed by the tensor product of the tensor of the vector basis of the chart. Here is another example. We contract B now with the vector V. That will give us a vector. The new indices are contracted, so there is a leftover new index here, which is downstairs. And you see that the components of B and the components of V have been multiplied and added in the correct way, so that the column here has the components of this one form after the contraction. And of course, we can use to basis expand to view this in a more geometric way. Now, let's also contract the other index. So B is now contracted with the vector V with respect to both indices, U and U. That will give us a scalar. It has the value 279 for those components. But instead of V, we could have also used W, which is an abstract vector, and obtain this expression here. Now we can use to basis expand, and you see that W has been replaced by a linear combination here. So this is not W, this is B contracted with V. And the remaining expression here involves contractions of the basis vectors with the vector W, and we can obtain a scalar expression by using the function contract basis, and that will give us the scalar that is this linear combination of the components of W. Now this is another example here. So we form this one form by adding this one form obtained by contracting B with V with respect to the index mu and multiplying it by the scalar 2 times S, and then the one form omega. Notice that the indices have to be written in a consistent way, and it's multiplied by the scalar expression 2 times scalar. So you see the final result here has a one form. The components here are written in terms of the scalars S and phi. And of course, if we want to, we can view it as a linear combination of the basis of one forms and have this expression displayed here. So let's see how to introduce a metric that will be used with this chart. So a metric, first of all, needs to define a U02 type C-tensor object. So let's see how to do this. So with this expression here, we define a C-tensor object with the name G, whose components are given by this diagonal matrix. So diagonal matrix is nothing but an ordinary Mathematica function that gives us a diagonal matrix with components in the diagonal given by this list here. So you see, this is nothing but the Schwarzschild metric in t, r, theta, phi coordinates. So you see, this defines the U02 tensor. So I forgot to mention that the fact that it is a U02 tensor here is determined by this list that refers to the basis. There are two minus signs here, which means that CTensor here has two indices which are both downstairs. Now, for writing better expressions later when using the function simplification, let's also write down the assumptions that we have both for the parameters and the scalar functions. So here we assume that mass is a positive real number. The scalar r is such that 1 minus 2m over r is positive, so that we are outside the horizon of a black hole. Theta takes values between 0 and 2 pi. Sorry, this is a mistake. Between 0 and pi. And phi takes values between 0 and 2 pi. Finally, we also mentioned that t takes values in for all real numbers. So that is necessary because there will be square roots involved in the expressions, and it's good that Mathematica knows all those assumptions. So after we have a U02 tensor object, we can tie it to being a metric. Sorry, let me first show you the metric here, how it looks like. So this is how it displays by using abstract indices. And here as a linear combination of the basis of the U02 tensors. Now, with the next call of the function set symmetric, we will tie this U02 tensor of being a metric for the specified chart. And this is done by calling the function set symmetric. Here it's called with 3 arguments. The first is the C-tensor object that corresponds to the metric. The second is the chart where the C-tensor object is defined with respect to the C-tensor object has been defined. And the last one is also very important, is the signature of the metric. And the signature of the metric is determined by this list of 3 numbers. And the first number here contains the number of plus ones in the canonical form of the metric. The second one contains the number of minus ones, and the third one the number of zeros. So this allows also the use of degenerate metrics, something that of course we will not use in this video. So we have chosen 3 plus 1s, 1 minus 1, and 0 zeros, which is a space-time signature with a convention of having the -1 for the time direction. So we call this function. Now, after g has been made the metric used in the chart, then automatically we have a covariant derivative, which is a Levi-Civita connection, and this will be defined by using the function cov d of metric. So sorry, the covariant derivative is not defined automatically. We have to use a call to this function to define it. So with this call here, we define the symbol CD to be used as the symbol of the covariant derivative of the metric, which is compatible with G and torsion free. And you see that this is an object that has a C-cov-D head, like this one. And it contains all the necessary information for computing with this covariant derivative. You see the first slot here has the parallel derivative with respect to which it defines Christoffel symbols. Then there is a C-tensor here. It has one index upstairs and two downstairs, so that is the gamma Christoffel tensor. I remind you that xTensor uses the philosophy of the connection coefficients are tensors with respect to which we express the difference between two covariant derivatives. And the last list here is the C-tensor object that corresponds to the metric. So all this is packed in the symbol CD. Now, there is a Levi-Civita tensor automatically defined. You see that this is a sparse array object, and it has 4 indices, as many as the dimensions of the manifold, which are all downstairs by default. Now, if you want to see all the components, you have to see the normal form of a sparse tensor object in Mathematica. These are not these are ordinary structures defined in Mathematica. It's nothing special for xTensor and xCoba. And you see now that this is a C-tensor that has all those components here. Now you see that some calculations have not been performed till the end, so I will also call the function simplify to see this in a more familiar form. Now you see the square root is not simplified, although this is r square. Sine theta is the determinant of the metric. Now the determinant of a metric is also a C-tensor object. You see here is its value, r4 sine square. You see it's a scalar, sorry, it's not a scalar, it's an object without indices. There's nothing in the list of components, but now you see that the third slot is not 0 because the determinant is a tensor density of weight 2. Now, if you just want to see the determinant without the C-tensor head, just add 2 square brackets in the end, and you will see the value of the determinant, but notice that this is not an ordinary expression, it has 2 tildes on top of it, which is the notation used by the xTensor package to indicate that we have a tensor density of weight 2 instead of a scalar. Now that we have a metric, we can raise and lower indices. So we have the vector v. Now, because we have a metric, we are allowed here to make new contravariant index by putting a minus sign here. Before assigning a metric, that would have produced an error. But now you see here the components of v as a one form. So let's look at that as an expansion and the basis. You see the one form produced by lowering the index of the vector has those components, and the original vector has those components, which are simple numbers. Now let's compute the contraction of omega and v like we did before. So that gives us a number. Now we know from differential geometry that this is equal to this. So if we exchange the upstairs and upstairs and downstairs indices, we should produce the same result. But, well, it's not, because computations are not finished. But if we simplify the result, we obtain -5. We can also contract v and w. W, you remember, is an abstract tensor object. So we have this contraction here displayed with abstract indices, mu and mu. We can expand it to a basis. Then we can contract the basis. And we can simplify. And that is a nice expression of the contraction in terms of the components of W. So let's look at our U02 tensor B. You remember that we defined it as a C-tensor object with those components shown here in the blue square. But now we can raise indices, like raise the index mu, put it upstairs, then we obtain an expression here that involves the inverse metric, and we can raise the other index as well and obtain that expression there. And we can simplify. Well, nothing much has happened. Now let's form the b square scalar. So we contract b mu nu with b mu nu by form b mu nu with indices upstairs and contract it with b mu nu. So you see that we obtain this expression here. Let's see if simplify will make this expression better. No. This is the metric, G mu nu. That is the original metric. But now we can write the inverse metric by simply erasing those, this is the metric here, and this is the inverse metric by raising the two indices mu and nu. And let's check what happens when we contract the indices of the metric. So we contract nu here and put a different index there, minus sigma. So we obtain this result. This should be, of course, the unit matrix, because we multiply G with its inverse to do the contraction. And we can see that after applying the simplify function. Now let's take a look at this expression here. So this should be V with its index nu lowered. Therefore this should give us a 0. Doesn't seem to give us the 0, but if we do some algebra, again, indeed we obtain something that is equal to 0. Now let's make an attempt to lower the indices of an abstract tensor. So we contract G and W with respect to the index nu. This is what we obtain. We expand in terms of the basis, and then we contract the basis. So this is the one form obtained by lowering the index of the vector W. Many times we want to do calculations involving the components of a tensorial object. One way to do that is to use the function ComponentArray. ComponentArray takes a tensor object, like for example V. We use its component indices here. That will give us, as we have seen, an output that is a linear combination of the bases. But if we actually want the components of V, which we can view here in the list of the C-tensor object, so if we want to extract this list and work with it, we can use ComponentArray acting on V. But for that to work, we have to put here a basis index inside here. So you see, this gives us a list of its components, which we can also view in a matrix form if we like. So after we construct a list of the components, we can use this list and manipulate it with ordinary Mathematica functions. So let me show you some more examples here. So these are the components of the vector V, Now we're going to compute the components. We're going to extract the components of the one form obtained by lowering the index of V. And you see that this is the list that we obtain. Now we can do that with the vector W. And you see we have used basis index here, and that will give us a list of components of W in the basis CH. Now this is another example here. You remember that U had been defined as 1 minus 2m over r times W. And here are the components of the U02 tensor B. These were defined to be just simple numbers, but we can also raise and lower indices. So we can take this expression here and raise the index nu. Be careful, we have to take out this minus sign and this minus sign so that the calculation is done correctly. So these are the components of B with a new index raised, that is a 1, 1 tensor. And we can raise also the other index by removing the minus signs from here and obtain this expression. Now, if we want to take more complicated expressions and compute their components using ComponentArray, we can use those expressions here, but they don't work because we obtain by putting here basis indices, we obtain expansions in terms of the basis. So in order to extract the components, we have to take that expression and apply on it contract basis. So this is the expression that we construct, and then with ComponentArray we obtain a list of its components. This is another example here. So now the index mu is raised and the index mu here is lowered, and we obtain the same result. But you see, the use of simplify is important. If we don't, then not all the algebra is performed. So let's see some examples with tensor products. So that is the tensor product of V mu times V nu. You see that their components are multiplied and only a list of their components is displayed. Now these are the components of the tensor product of V and W. W is a tensor object. So you see the components of W written here in the CH basis, and the tensor product of two tensor objects, W with itself, and that will give us a 2-0 tensor where you see all the components are multiplied with each other. Now be careful, this is not very nice, but you will encounter it in many expressions here. You see that in the diagonal we have W0 square, W1 square, W2 square, and this sometimes might not be so obvious and differentiated for something that is W02, where 0 and 2 are the indices. But we have to look at those expressions closely, and of course if it doesn't make sense, we will understand that the correct way to see this is that W0 is multiplied with itself. Now let's see how to extract the determinant of the metric as an ordinary function. So first we form a list with the components of G. So if you write this in a matrix form, these are the components of the metric as a list. So now such a list is interpreted by Mathematica as a matrix, and we can use the ordinary det function applied on this matrix to obtain just this simple expression for the determinant of the metric without being marked as tensor density, as it will be done with the function determinant that we showed before. Of course, we have already seen it, but let's show some examples. We can obtain specific components using components indices. So if we use a component index in the vector v, we obtain the first component. Notice here the minus sign lowers the index of v. That's why we have 1 minus 1 over 1 minus 2 over r. If there is no minus sign, we just have the component minus 1. So similarly, we can obtain the 2 component of the metric with this expression here. It's equal to r squared. If this is 0, the corresponding component is 0, but if this is also 0, it is minus 1 plus 2 over r. And we can obtain all the components in a list. This will have the same effect as using component array that we have used above, but here we use explicit component indices. Sorry, these are just the diagonal elements, I'm sorry, so it's not the same as component array. So here we form a list of the diagonal elements of the matrix, of the metric. And this is an expression that will give us the inverse metric components. So you see, if I remove the minus signs from here, then I obtain the diagonal elements of the matrix of the components of G. Let's make a small digression now and remember how to apply rules in expression that make substitutions. So you remember when we were discussing the xTensor package, we discussed the use of the function makeRule. And makeRule here takes a list and it substitutes the first element with the second element of the list whenever it is found in an expression. So let's form this expression here. So that is the contraction of W with itself. But now let's apply the rule that W mu will be replaced by V mu. So you see, this rule substitutes W mu, but it does not substitute W minus mu. I can make a further substitution by adding another rule that replaces W minus mu with V minus mu. And that gives us the contraction of V with itself. That is the norm square of the vector V. Now what we usually do is we give names to the rules. And we have complicated calculations to do. So that is the UW rule, the VW rule for upstairs indices, and that is the VW rule for downstairs indices. And then we can take this expression here and start manipulating it using the rules. So here I can apply the upstairs substitution rule. That gives us what we had obtained before using this expression. And then in the result I can make another substitution using the downstairs WV rule. So let me now define some more tensors to play with. Xi here is a one form. This is determined by the second argument of the C-tensor function here, and its components are the ones shown in this list. Now F here is a 2-0 tensor with two indices upstairs, and its components have been written in this matrix here, and you see that I have defined F to be an antisymmetric tensor, because you see the components here differ only by a minor sign. So then I display the components of the two new tensors using ComponentArray. So you see Xi here has those components, 1 over square root 1 minus 2 over r, square root 1 minus 2 over r and r cos theta. And F is an antisymmetric tensor with components 1 minus 2m over r in the 0, 1 position. 1, 0 position is minus that, and cosine theta in the 0, 3 position. Now the reason I defined those tensors is to check whether xCoba will detect the antisymmetric properties of F, and for example compute expressions that contract antisymmetric and symmetric tensors, which would give us a 0. So let me form this expression first. So I take f and I contract it with xi, with two x's. So f is antisymmetric, this tensor product is symmetric, the result should be 0. Well, it's not obvious that it is. But if the expression is simplified, the result is 0. Now, this is another expression here. F is antisymmetric, but B, you can check that I cunningly defined it to be symmetric before. So this result should be 0 too. Again, it's not obvious unless I apply the simplify function. Now, this is another expression involving antisymmetric contraction of antisymmetric and symmetric indices. So I take the Levi-Civita tensor here and contract it with the new indices of B. So this is B with its indices raised. And I obtain 0 immediately. Now, let me contract epsilon with f with respect to the first two indices of epsilon. This is of course not 0 because mu and nu are antisymmetric in both tensors. So look at this expression here, it has some disks here because the expressions are considered to be large. So if I hover with the cursor over the blobs, I can see the algebraic expression that involves them. But I can do better if I apply the simplify function, and then we obtain simpler expressions. So now let me take this expression here and also contract the remaining indices, rho and sigma, and that should give 0 also, okay, because they are antisymmetric, but the product is symmetric here, so, well, you can check yourself. We obtain 0 immediately. This is another example. So here I contract mu and nu with an antisymmetric object, and rho and sigma with a symmetric tensor product, and we obtain 0 immediately. So let's see now how to work with covariant derivatives. The notation for covariant derivatives is similar to the one used in the xTensor package. So if we want to differentiate a vector, we put the symbol of the covariant derivative that we have defined before, the index here with respect to which we are differentiating, and inside brackets we put the tensorial expression that will be differentiated. Here we just compute the divergence of the vector v, that is a scalar. Another way to act with the derivative is to use the map add symbol of Mathematica. And we obtain the same result. As we have already mentioned, the covariant derivative associated with the chart with the metric is a Levi-Civita connection, so it is compatible with the metric. So the covariant derivative of G min E, or its inverse metric here, are both 0. Now let's see how it differentiates an abstract tensor. So the output form here, the standard form, in fact, uses this symbol here for the covariant derivative, and if you hover above the symbol, you can see the details of the covariant derivative. But you see, this is a similar expression as the one obtained with the xTensor package. Now let's differentiate the one form. We use different indices here, so that will be a U02 tensor. Now this expression here is long, so it's hidden under the blob, but you can simplify the expression here, and still we haven't seen it anyway. Now this differentiates the tensor F. That is a 2-1 tensor. More stuff. Or we can contract some index of F with that of the covariant derivative, and then we obtain a vector. We can also compute second derivatives of C-tensors, the same way that we did with the xTensor package. That is a 1-2 tensor. And this is another example where we contract the index of the differentiated vector with the index of the first derivative, and we obtain the vector, sorry, the one form shown here. The Christoffel symbols of the connection can be displayed by using the function Christoffel. So just look at the arguments here. There are two levels of arguments. The outer level here has the indices in the abstract index notation. The ordinary Christoffel symbols have the first index upstairs, the other two are downstairs, and those arguments here show us determine which connections, Christoffel symbols, we want to, and with respect to which connection. And PDCH, as we have already said, is the partial derivative connection associated with a chart CH. So this is the result here. So we can see all the components of the Christoffel symbols for this metric. And if we want, we can compute the Christoffel symbols with the index mu lowered and obtain this expression here. So the Christoffel symbols are ordinary C-tensor objects and can be used in tensorial expressions. So this is an example where we contract the last two indices of the Christoffel tensor here with v nu and v rho. That gives us a one form. We can simplify this expression here. That will give us something easier to read. And we can also obtain the components of the Christoffel symbol in the ordinary list by applying the function ComponentArray. Now we have to use basis indices Sorry, I forgot a comma here. So these are the Christoffel symbols in an ordinary list, and we can display it in matrix form so that we can look at them in this way. Finally, let's look how we can obtain information about the curvature of the metric. The basic object for curvature is the Riemann tensor. Now, as we have explained in detail in the xTensor video, xTensor and xCoba define the Riemann tensor to have the first three indices downstairs and the last one upstairs. It doesn't really matter very much if we can raise and lower indices. So now we can see the components. Of course, this is an abstract tensor. It carries indices mu, nu, rho, and sigma. And similarly, but trivially in our case, we can have the Ricci tensor, which of course for the Schwarzschild metric it is 0, as well as the scalar curvature. That is also 0. But for other metrics, we will obtain the corresponding expressions. The Einstein tensor, also equal to 0 in our case. The torsion tensor is also present, but it is trivial for a coordinate basis. But the Weil tensor is not so trivial. See, we write the expression for the Weil tensor with all the indices downstairs, and here we can see all its components. And in fact, for the Schwarzschild metric, we can check that the Riemann tensor and the Weil tensor are equal, and we see that this is true in the particular chart that we have chosen. Of course, then it's true in any other chart. The Kretschmann scalar, that is the R² scalar, we know very well it has this famous form. We have seen it in another video where we were computing the curvature tensors for the Schwarzschild metric, but not using xCoba. And you see that this is non-zero, and it is singular as r goes to 0, goes as r to the 6 to infinity, blows up as r to the 6 as r goes to 0, which indicates that the Schwarzschild metric is singular at r equals 0. Now, this is the definition of the Riemann tensor in the conventions of xCoba. As I have already mentioned, it follows the book by Wald. So this is how it is defined. So let's compute the commutator of the derivatives. We do the same thing as we have done for in the xTensor package. We act twice with the covariant derivative, and then we commute the indices of the derivatives here. Now this is the result. We can simplify it, obtain something simpler, and let's define this to be the symbol COMM from the word commutator. Now, this is the contraction of the Riemann tensor with the vector v, as it is done in this expression here. We contract the index delta. So this gives us this result here. Let's call this result RIEM. So RIM and COM are objects that are CTensor objects, and we can check whether they're equal. So on the surface it seems like they're not equal. Then we apply simplify, and we find that the equation is true. So they are actually equal to each other. So very briefly, let me close this video by showing you how to manipulate basis vectors. So we have seen the basis vectors to appear in expressions. So these are stored in special symbols, and these symbols have the head basis. And the head basis here, first it has a component index, so for example 0. Then we specify that this is downstairs basis index, and then the abstract index mu specifies that this is a vector, and it gives us E0 mu. And by changing this number here, you can obtain any other basis vector, or if you like, as a table, have a list of all the basis vectors, E0, E1, E2, and E3. We can also have the co-basis. So in order to obtain the co-basis, we have to put this index upstairs instead of downstairs, and the abstract index mu to lower it and make it downstairs. So that will give us the co-basis. And basis array is a function that gives us here the tensor product basis. E0, E0, E01, E0, E02, E0, E03, etc., etc. So, of course, since they are dual bases, they should contract to each other, and the result should be Kronecker delta. Let's check this. So we form all possible combinations of contractions of basis I with basis j. For it to be a construction, this index must be upstairs, this index must be downstairs, and also the component index must be compatible with this choice. So we form the contraction, and then we have to put here contract basis in order to compute the contraction for each pair. And indeed, you see that we obtain the Kronecker delta. Now, if we had not put here contract basis, then the result would have been this one. So let's play with this and check the fact that the components of tensors in a basis are actually the contractions of the objects with the respective basis vector or covector. So let's take this expression here, which we have already seen, that gives us the component 1, xc1. Now we contract xc with the first, with the e1. This is the result. And if we force the basis to contract, we obtain the same result. Similarly, this is the 1,2 component of the B tensor. It is equal to 5. So this component should be obtained by contracting the 1 and 2 basis vectors with the tensor B. That gives us this result. And when forcing the basis to contract, we obtain B12. Now let's play with the metric here. So we take the metric and we contract it with EI and EJ for all possible combinations of I and J. So you see that we obtain a matrix which has as elements the components of the metric. Now let's compute the covariant derivatives of the basis vectors. Here is one example. So that is the covariant derivative of E1. That is the covariant derivative of E2, co-basis vector. That is the covariant derivative of the tensor product of E2 and E0. Now that is the second derivative of E0. And that is the second derivative of E1.